2 years ago or so, we passed through the petascale benchmark. We are now on our way to exascale, but as you will hear from all of us, this is a journey. This is a stake in the ground, but it's going to be a journey to get there, because there will be not only opportunities that arise because of this increased computing capability, but there will be challenges along the way, and those challenges are not insignificant. As Dr. Jacobs mentioned in her remark, we won't get there by business as usual approach. There has been a fundamental change in the underlying technology used in computing, and the pathway to exascale is something that is not straightforward, but it is something that we can certainly address. I thought it might be worthwhile just to, since I'm the sort of the opening act in all of this, I thought it might be worthwhile to at least tell you a little bit about the role that current extreme scale computing, that is petascale and beyond, plays both in science and in industry, and then tell you a little bit about what the current state is, and then a look into the future. I'm going to primarily set up the following speakers, so I will cue them on various slides so that you can anticipate what it is that they're going to be discussing. But one of the things that extreme scale computing provides us is really a way to look at the world around us in a new way. Astronomy is in the process of becoming the first digital science. You might think that astronomers currently go to the mountaintops and actually look through their telescopes at the universe, but they don't. It's all done digitally. There is a camera behind that telescope, similar but much larger than the camera you have in your digital camera today, and it's the analysis of that digital information that gives us new insights into the structure and organization of the universe. That's complemented, of course, by computational studies that are modeling the evolution of the universe. What the James Webb Telescope will see, there are modelers right now simulating that, so they'll know much better what it is that they'll be finding. We also certainly see in the world today, whoops, do I get rid of it? Nope. Okay, bring it back. In the world around us today, there are modelers looking at simulating, modelers looking at simulating tornadoes, simulating hurricanes. All of you remember Katrina, I'm sure. Probably very few of you remember Rita, which was the hurricane right after Katrina. Initial projections were that it was going to hit the city of Houston dead on. It led to basically massive panic in the city of Houston, and the whole city came to a grinding halt as people fled the city and ran out of gas on the clogged freeways exiting Houston. Clearly, a better capability of being able to predict those kinds of phenomena are going to be extremely important, not only from a scientific point of view, but from a societal point of view. And finally, there is this fascinating world of the nanoscale, where the classical mechanics that we're familiar with in the real world meets quantum mechanics, that very weird mechanics that occurs when objects get to be extremely small. But as esoteric as that is, of course, this underlies genomic biology. It underlies the march toward personalized medicine. So it also has not only scientific, but also tremendous societal benefits. And of course, industry is more and more using high-performance computing to design better products, whether it's Boeing designing the wings on the 787, the Dreamliner, where rather than the normal 70 to 80 designs that they actually have to put into a wind tunnel, they were able to reduce that to the order of 10 designs that had to be tested. Procter & Gamble. One wouldn't imagine necessarily a company like Procter & Gamble investing heavily in high-performance computing, but they had a problem with one of their products, Olay. It was separating into two distinct phases, something that's considered to be a no-no in that industry. It was through supercomputing that they actually determined how it is that they could redesign that product so you would no longer get that separation. And of course, Rick Arthur, in a few moments, is going to tell you a lot more about how General Electric and other companies use high-performance computing. Extreme scale computing today. Clearly, there are groups out there. I know a quadrillion arithmetic operations per second may sound boggling, but there are science groups, there are industrial groups right now that need that kind of capability. Whether it is designing new fuels to go in engines, redesigning the engines to make optimum use of those fuels, and sometimes very small changes in the fuel can have huge impacts on the performance of the engine. For example, octane rating. This is the molecule that defines the octane rating of 100. You change this molecule to that molecule, you get an octane rating of 0. You put N-heptane in your automobile engine, it's going to shake your engine apart. So clearly, we need, as we develop new biofuels, we need to understand the impact that those biofuels will have. Who needs petabytes? Again, it's hard to imagine somebody would need that much storage, be producing that much data. But in fact, the Large Synoptic Survey Telescope, which is a project that NSF is considering, is going to be producing 15 to 20 terabytes of data per night, which will give rise to 100 to 200 petabytes of data over the course of its first 10 years of operation. So clearly, hundreds of petabytes of data are going to be needed for those types of projects. And the Square Kilometer Array, which is an international project, is looking at 100 to 10,000 times that amount of data. What did today's petascale computers look like? I always say that although Jaguar is #2 on the top 500 list, it's still the #1 machine as far as science and engineering goes. The Chinese have built a very powerful machine, but it really has limited applicability to the types of science problems that you see represented and the types of industrial problems that you see represented in this panel. Clearly, peak performance is already exceeding petaflop, tremendous number of processors, tremendous amount of memory that's associated with each of these machines. Just to give you a little exercise here to make you understand what it is these numbers talk about, if you could take a calculator and enter one 14-digit number, hit the multiply sign, enter another 14-digit number, hit the equal sign, if you could do that in 1 second, which you clearly can't, then it would take you 32 years to complete 1 billion calculations. That's a gigaflop. It would take you 32,000 years to complete a teraflop. It would take you 32 million years to get to that petaflop, and there's not enough time in the existence of the universe to actually get to a exaflop. So let me talk just briefly then about exascale computing tomorrow. Clearly, the impact of exascale computing is going to be huge. There is a broad range. Unlike many other technologies, computing technologies affect all of science. And there is a broad range of science that can be tackled with these types of machines, whether it's problems in biology or problems in public health, earthquakes, everything in between that is impacted. And Dr. Zachariah is going to be talking about that topic in more detail. Here's the problem. We took Blue Waters, which is at 10 petaflops, and we scaled it up to an exaflop. What would it require? Well, it would require a gigawatt of power just to run that system. It would require something on the order of 1 million square feet to hold the computer itself. And scientists would be struggling with concurrency that's in the billions, not in the millions that we see right now. So this is the fundamental problem that faces us, and you're going to hear a lot more about this from Dr. Yellick. Finally, this article was published back in February by Peter Koge, actually a very careful look at what the situation is in supercomputing at the time, and he noted that supercomputers are now running our search engines and social networks. but the heady days of stunning performance increases are over, and Kathy Yellick is going to talk in much more detail then about what the situation is and how we might move forward from here. Thank you.